Hey there, it's Shannon MATHCHICK Myers, and today we'll be looking at improper integrals. So let's warm it on up and consider this function f of x is equal to 2 over x cubed. So graphing, let's see what we'll have. Let's label our axis, -5 to 5, so each line will be a half unit, and then this one it's going to increase pretty darn quickly and decrease pretty darn quickly. So each box will be 2 on the vertical axis. And then going to our graph, I'll enlarge the graph a bit. When x is 1, we would get an output of 2. When x is 2, we'd have 2 over 8, which is a quarter. So that's going to, decrease really quickly here. And let's take a look at when x is a half. Do you see you'd get 2 over an eighth, which would be 16, so you'd be way up here already. And then it just goes further from there. So you end up closing out pretty quickly after 1. And then you have all this going on, kind of like this. And then this graph will reflect on the other side. So again, it closes out real quickly. And then it's gonna just, I'm gonna graph my other point here. So we'll have at -1/2 will be up or down at -16. And so then it decreases super quickly. So if you were to think, oh, okay, this is, let's just say here's some b to the right of 1, right? Because we know that it starts kind of a closing out behavior, right, when x goes to the right of 1 or to the left of -1, correct? We'll just look at that positive side. And here, if we think about, what's going on, would you agree that the indefinite integral of 2 over x cubed with respect to x is just fine, right? No issues. But if we look at the definite integral, and we start that definite integral at 0, there's an issue, right? Because isn't there a vertical asymptote at x equal to 0 here, right? So this definite integral from 0 to 1 of 2 over x cubed with respect to x has a vertical asymptote at x equals 0, that vertical line. So there's a bit of a problem, right? There's an issue. Cool? Okay, so now let's explore a little bit, right? Let's find the limits. For this case, it's okay. We just want to see where this graph is going. So if you get an infinite result, you can write positive or negative infinity. So let's take a look. Looking at our graph, as x is approaching 0 from the right side, and you trace your graph, what's happening? Do you see how it's increasing without bound, right? So we would end up with a result of infinity, so that finite limit would not exist, right? But as x approaches infinity, right, so now as we're looking to the other side, what would you say that answer is? Good. As x is approaching infinity, the y values are approaching 0. They never quite reach it, even though it kind of looks like it, but that's what's happening. So let's evaluate this definite integral here, all right? So this will be equal to 2x to the negative 2 over negative 2, evaluated from x equals 1 to x equals b. Cool so far? The 2's divide out, and we would get a negative on the outside. We would have 1 over b squared, and then minus 1. These 2's divided out. And then if I flip that, distribute the negative through to make it look pretty, I would have 1 minus 1 over b squared as my result. Cool with that? Excellent, excellent. So now, keeping that in mind, all right, let's put some stuff together. Recall that if a function is non-negative on the interval, closed interval from a to b, the definite integral is equal to the area under the curve and bounded by the x-axis, and of course x is a and x equal to b. Also remember that a function is said to have an infinite discontinuity at c when from the right or the left the limit doesn't exist. So if you have the limit as x approaches c from the right of f at x equal to plus or minus infinity, or the limit as x approaches c from the left of f at x equal to plus or minus infinity, then you've got a discontinuity, you've got a vertical asymptote there. So let's look at this integral. Okay, so now we're playing around, we've been playing around with this, right? We know what the definite integral from 1 to b is. We also, so we'll use that. And we also graphed it. Let's graph it on this grid really quickly. If you recall, there was an ordered pair at 1, 2, and then we don't need to worry about to the left of 1. Let's see, when x was 2, what did we get? A quarter, right? So it'd be about here. And it'll go and close out pretty quickly. Cool so far? All right, so what we've got here is a situation where we want to know, is this area going to close out fast enough, right? In order for us to be able to have a limit that exists when we evaluate the limits on this definite integral. Groovy? All right, perfect. So now let's do it. So basically here we don't want to put infinity in there. So if we looked at the limit, I'm not going to put what we're approaching yet. Let's say we went from 1 to b of 2 over x cubed, right? And then b would be approaching what? Awesome, infinity with respect to x. Now, we know that this is equal to, actually, we've got that improper integral, improper because we have an infinity as a limit, is equal to the limit of the integral from 1 to b of 2 over x cubed dx. This in turn will equal to the limit as b approaches infinity up. So we know that we got 1 minus 1 over b squared from our warm-up work. And remember, we did the work in the warm-up problem, all right? So here, well, what will this limit be? if I plug in infinity, notice that we'll have, I mean, you don't really plug in infinity, but as b increases without bound, that fraction part will go to 0, and so we'll just get 1 minus 0, which is 1. So what did we find out? We found out that the integral from 1 to infinity of 2 over x cubed with respect to x converges, and it converges to 1. Cool, cool? All right, so let's look at the official rules here. If we suppose that f is continuous on the interval from a to infinity, then this integral, just like we had done before, we would have the limit as b approaches infinity of the integral from a to b of f at x dx. Groovy? Just did an example. Now, suppose it's going the other way. F is continuous from minus infinity to b, inclusive of the b. So now we would take the limit as a approaches negative infinity of the integral from a to b of f at x dx. Now, suppose f is continuous on the interval from minus infinity to infinity. Then we just break it up. So we would say that this will be equivalent to the limit. And then again, a lot of times I'll put the limit in after, once I set it up. You can always break up a definite integral, right? Have another limit here, and this integral will go from c to b of f of x dx. Okay? And so, for this one, we will have the limit as a approaches negative infinity, and for the second one will be the limit as b approaches infinity. Cool, cool? So we're just splitting it up into 2. All right? Now, where c is any real number, just pick something easy, right? In the first two cases, the improper integral converges when the limit exists. Otherwise, the improper integral diverges. In the third case, the improper integral on the left, so we're talking about this one, diverges when either of the improper integrals on the right side, either one of these, it could be this one or it could be this one. You don't want to figure both of them out if one of them ends up diverging, because what happens is you end up with an indeterminate form. Okay, that's why this is important. And so if either one of the improper integrals on the right diverge, then the one on the left diverges. Now, otherwise, it converges to the sum of those two limits. All right, so let's check it out, okay? I always, like looking at a picture of what we're working with. And so on this one, we've got the integral from 1 to infinity of dx over x. So if x is 1, right, I'm drawing the graph of the integrand. If x is 1, we get an output of 1, right? And then as x gets larger, so when x is 2, we get an output of a half, third, a quarter, etc. And so we'll end up with something like this. And what you'll notice is, you'll notice that it's not closing out as quickly. And so we're looking at this region here, and what I'm seeing is that it does have a horizontal asymptote, but it's not reaching, it's not closing out quite as quickly as the one we worked with before. So, using our definition, this will be equal to the limit as b approaches infinity of the integral from a to b of 1 over x dx. That in turn equals the limit as b approaches infinity of. So this is going to be natural log at absolute x. It's going to go from x equals 1 to x equals b. And then we will have the limit as b approaches infinity of natural log. We can just say b because b, we're heading to the right of 1. So natural log at b minus natural log at 1. Well, we know natural log at 1 is 0, and the limit as b approaches infinity of 0 will be 0. And so now we have to look at what's happening as b approaches infinity. So when you put in ever larger numbers into the natural log function, what do you start getting out? So let's just take a look. We'll clear this one, and then we'll just go to natural log at x and graph. And do you see that as we go more and more to the right, see we're plugging in 100, it doesn't stop increasing. You go to, see, you go all the way to 300, it's a little bigger than it was at 100, right? So it actually ends up going to infinity. So we would end up getting infinity minus 0 is still infinity, meaning that it's gonna, it's gonna diverge, okay? And so what would we say for our result? We would say, so the integral from 1 to infinity of dx over x diverges. And that's it. So that tail piece didn't close out fast enough to get a convergent integral. Okay, so let's see what this graph looks like. We've got 4 plus x squared as a denominator. And so, and we're going from minus infinity to infinity. So I don't think it's going to get very high. So I'm going to just set it from -1 to 1 on the axis, the y-axis. And then on the x-axis, let's give it -5 to 5. That should be good. All right. So we have x and we have y. Groovy? And then I'm going to plug in x equal to 0 because I think that's a good number for us to split the integral up at. And when x is 0, do you see you get a quarter? And then as x gets larger, when x is 1, you get a fifth, which is just below, right? That quarter, when x is -1, you'll be just below that quarter. And then when x is 2, it's really going to close out because you'll get 2 squared is 4, 4 plus 4 is 8, so it's much, much closer to the axis when you're talking about plus or minus 2. So it's going to look something along these lines. graph will be something along these lines. Sorry, my puppy's barking. Got my little pup going on here. And then, so I think this one will work because look, it closes out really fast. So let's see what we end up with, okay? All right, so now, here we go. We're gonna need to split up this integral as the limit as a approaches negative infinity, and then we'll go from a to 0. So my c is going to be 0 from the formula. And then I have my dx. I'm going to set it up as my arctangent. That's 2 squared plus x squared. And then plus the limit as b approaches positive infinity of the integral from 0 to b of dx over 2 squared plus x squared. Groovy? Awesome. So this will be, in turn, the limit as a approaches negative infinity of the arctangent. My a is 2, so we'll have 1/2 arctangent at x over 2 evaluated from x is a to x is 0, and then plus the limit as b approaches infinity of the integral from 0, no, sorry, we're doing the integral, the same indefinite integral here, or the same, sorry, antiderivative, 1/2 arctangent at x over 2, and then that's going to go from x equals to 0 to x equal to b. Groovy? Okay, so let's see what we got. This will be equal to the limit as a approaches negative infinity of 1/2 times arctangent at a over 2, nope, sorry, arctangent at 0 over 2 plus arctangent at a over 2 plus the limit as b approaches infinity of 1/2 times arctangent of b over 2 minus arctangent at 0 over 2, which is the arctangent at 0 is 0. So this right here, whoops, this will be 0. And then, sorry, this should be a minus. And then this one will be 0. And the limit as anything, you know, as whatever approaches infinity of a constant is just that constant. So we will end up with the arctangent graph. So here, just in case you didn't remember it from Calc 1, if we go to y equals, we clear out, and we go to second tangent, and then our tangent, it's going to be x over 2, and we will graph, and let's see what's happening, right? So notice as you go infinitely to the left, right, what output are you approaching? Do you remember the bounds for your inverse tangent function? Excellent. You're going to get 1/2 times negative, actually it would be negative pi over 2, right? because it's 0 minus pi over 2. And then on the other one, we would get plus pi over 2 times a half. So putting this together, we'll get pi over 4 plus pi over 4, which is 2 pi's over 4, which is pi over 2. So what did we find out? We found out that the integral from negative infinity to infinity of dx over this, actually it wasn't square root, my bad, over 4 plus x squared converges to pi over 2. Cool, cool? Excellent. All right. So, next up, let's see what we have. Ooh, fun, more rules. Aren't you excited? All right, improper integrals with infinite discontinuities. So this one, the notation's a little weird. Just remember C is a number that you plug in, okay? So C ends up being kind of the problem child. So suppose f is continuous on the interval from A, non-inclusive, to B, inclusive, and has an infinite discontinuity at x equal A. Then what's going to happen is we're going to get the limit as A approaches C from the right side of the integral from C to B, f at x dx. Now, suppose f is continuous on the interval where A is included but B is not, and it has an infinite discontinuity at x equals B. Then what will happen is we'll have that limit as this time B will be approaching C from the left side, and that's going to go from A to C. And that's f at x dx. Now, suppose that f is continuous on the interval from, I don't know, from A to B, inclusive, except somewhere, within the graph. Some C in that closed interval from A to B, at which f has an infinite discontinuity at x equals C. Then what we do is this. We split it up. We have the limit as B approaches C from the left side, the integral from A to C of f of x dx, plus the limit as A approaches C from the right side of the integral from C to B of f of x dx. In the first two cases, in the first two we did without the sum, the improper integral converges when the limit exists. Otherwise, the improper integral diverges. And then again, you just work, if one of them diverges, then the improper integral diverges. Otherwise, you'll get the sum of the two limits. So now that you've learned about all these things, you just have to be real careful about how you approach definite integrals. You have to make sure there's no discontinuity on the interval of interest. So here, I'll check the endpoints first. When I plug in a 3, I'm good in my denominator, right? 36 minus 9 is fine. But when I plug in a 6, do you see I zero out my denominator? So there's a discontinuity, and it's non-removable at x equals 6. Cool, cool? All right, so that means that this is an improper integral, and then I'll have the limit as b is approaching 6 from the left side of the integral from 3 to b of dx over the square root. I'll set it up for our arc sign of 6 squared minus x squared. Now that in turn will be equal to the limit as b approaches 6 from the left side of arc sign at x over 6 evaluated from x equals 3 to x equals b. Cool so far? Awesome. And then we'll have the limit as b approaches 6 from the left of arc sign at b over 6 minus arc sign at 3 over 6. Now this will give us the limit. Actually, we can go to directly substitute. So we'll get arc sign, because there's no issues here in plugging in 6. So we just go 6 over 6 minus arc sign of 1/2. 6 over 6 is just 1. Arc sign at 1 is pi over 2. And then arc sign at pi over 6, sine at pi over 6 has an output of 1/2. So arc sign of 1/2 is pi over 6. And then combining them, we'd have what? 3 pi over 6 minus 1 pi over 6 is 2 pi over 6, which would give us pi over 3. And so the integral from 3 to 6 of dx over the square root of 36 minus x squared converges to pi over 2. Cool, cool? All right, and then let's go ahead and take a look at this one. So I check the endpoints. When I plug in 0, I'm fine. I don't zero out. When I plug in 2, I don't zero out. But there is something in the middle that's bad, right? There's a discontinuity at x equal to 1, correct? And so I have to split this integral. So this would be the integral from 0 to 1. I'm going to write this as x minus 1 to the negative 2 dx plus the integral from 1 to 2. Again, rewriting the integrand. Now, here we go. This will be the limit as b approaches 1 from the left of the integral from 0 to b of x minus 1 to the negative 2 plus, with respect to x, can't forget that, plus the limit, now a will be on the right side, so a will be approaching 1 from the right side, and we'll be going from a to 2 of x minus 1 to the negative 2 dx. Good so far? Excellent. So now, evaluating that integral, do you see, well, first we'll put our limit notation. B is approaching 1 from the left side, and then we're going to get negative 1 over x minus 1. That will be evaluated from x is 0 to x is b, plus the limit as a approaches 1 from the right, I'll start to work it out, of negative 1 over x minus 1 evaluated from x equals a to x equals 2. So now, here we go. This will be, with direct substitution, actually I won't directly substitute. Let's look at the graph, and then we will, we'll find the limit graphically. So we'll clear that out, we'll go to our y equals, we'll clear that out, and then we're graphing negative 1 divided by x minus 1. Graphing our result. So we can look at the limit. And what happens as we approach 1 from the left side? We'll look at that one. So as we approach 1 from the left side, we increase without bound, correct? So this will be equal to infinity. This first part will be equal to infinity minus minus is plus, and then you'd have another negative, right? 1 over negative 1, which is still infinity, which is a sign of divergence. So we ignore this one, don't do this one, do this one, because you'll probably get an indeterminate form. We only need to show one of the limits going to plus or minus infinity, not existing, in other words. And so what we found out was the integral from 0 to 2 of 1 over x minus 1, the quantity squared, dx, diverges. Cool, cool? All right, and that wraps up this video. I hope you had a wonderful morning, afternoon, or evening whenever you watch this show. And if you like what I'm doing, go ahead and share the video, subscribe to my channel, and hit that like button. Bye.